Good day everyone, my name is Kanishk Jagtap and today we will talk about photochemistry and Jablonski diagram. First of all, photochemistry is defined as the study of chemical reactions that proceed with absorption of light by atoms and molecules. Photochemistry has an immense importance in our day-to-day life as well as in chemical industry. Let us walk through some examples. Photosynthesis is the process in which plant uses solar energy to convert carbon dioxide and water into glucose and oxygen isn't possible without light. Magnesium is the powerhouse behind photosynthesis in plants. Without magnesium, chlorophyll cannot capture sun energy needed for photosynthesis. Another example is of bioluminescence, the process of production and emission of light by living organisms. For example, in fireflies, anglerfish and other creatures, an enzyme luciferin is present in the abdomen that catalyzes a reaction that produces light. Here, luciferin reacts with oxygen to create light. In humans, many photochemical reactions takes place, such as human formation of vitamin B, also known as cholecalciferol, by exposure to sunlight. Vision is also initiated by photochemical reaction of rhodopsin pigment. Photochemical production of artemisinin, an anti-malaria drug, has been a major weapon in the fight against malaria worldwide. In chemical industry too, many photochemical reactions takes place such as polymerizations which are started by photoinitiators which decompose upon absorbing light to produce the free radicals for radical polymerization. Here monomers and oligomers which are low molecular weight polymers and photoinitiators undergo induced polymerization upon absorbing light. Similarly, in photoalkylation, it is used for light-induced addition of alkyl molecule or alkyl group to molecules. Photodegradation, which is also known as breakdown of compounds under, such as polyvinyl chloride under light. As a result, medicine bottles are often made with darkened glass to prevent the drugs from photodegradation. Now, as said earlier, photochemistry has a variety of applications. Now, let us turn our attention towards Jablonski diagram. Jablonski diagram is the pictorial representation of electronic states of a molecule and the transitions between them. Before that, we will try to understand the spin multiplicity of a state. Most molecules have an even number of electrons in its ground state and all the electrons are spin paired. The quantity 2s plus 1 where s is the total spin is also known as spin multiplicity of a state. As seen in figure 1, when spins are paired, the upward orientation of electron spin is cancelled by the downward orientation so that s is equal to 0 as s1 is half and s2 is minus 1 by 2. So s1 plus s2 is 0. Thus 2s plus 1 is 1 and spin multiplicity of a molecule is 1. And we can say that the molecule is in singlet ground state. Now upon absorption of photon of a suitable energy Hv, one of the unpaired electrons goes to a higher energy level or an excited state and the spin orientation of two single electrons may either be parallel or antiparallel. As seen in figure 1, here spin is antiparallel. Therefore, S1 plus S2 will be 0. Thus, 2s plus 1 is 1 and spin multiplicity of a molecule is 1. So we can say that the molecule is in singlet ground state. Whereas in figure 3, the spin are parallel. Therefore, S1 plus S2 is 1 and thus 2s plus 1 is 3. The spin multiplicity of a molecule is 3 and we can say that the molecule is in triplet ground state. Now, since the electron can jump to any of the higher electronic state depending of the energy of photon absorbed, we get a series of singlet excited state Sn and triplet excited state Tn, where S1, S2 and S3 are known as first, second and third excited state respectively, whereas T1, T2 and T3 are known as the first, second and third excited state respectively. Now, one thing of immense importance is for each singlet excited state, there will be a corresponding triplet excited state and singlet excited state will have a higher energy than the corresponding triplet excited state in this series as seen as Es1 will be energy of S1 will be greater than energy of T1 and so on. Now on absorption of photon or the light photon, the electron of the absorbing molecule will jump from S1 to S1 or S2 or S3 singlet excited state depending upon the energy of light photon absorbed. Now this will give us the equation A plus HV is equal to A star, where A is the molecule in ground state, HV is the molecule in light energy, and A star is the molecule in its excited state. Now this activated molecule will return to ground state by dissipating its energy through two type of processes, that is non-radiative processes and radiative processes. First of all, we will talk about non-radiative processes. These processes involve the return of activated molecules from the higher excited state S3, S2 or T3 or T2 to the first excited state S1 or T1. These processes do not involve emission of any radiations, therefore called as non-radiative processes or radiation-less transition or processes. Here, energy of the activated molecule is dissipated in form of heat through molecular collisions. Then the process is defined as internal conversion process or IC. And this IC process occurs in less than 10 raised to the power minus 11 seconds. Now, the molecule may also lose energy by another process known as intersystem crossing or ISC, which involves transition between states of different speeds, that is different multiplicity, as for example from S2 to T2 or S1 to T1. These transitions are also non-radiative and radiationless, but spectroscopically such transitions are forbidden. However, they do occur at a relatively slower rate. Now, let us talk about radiative processes or radiative transmission. Those are mostly fluorescence and phosphorescence. These transitions involve the return of activated molecule from singlet excited state S1 or triplet excited state T1 to ground state S0. Such transitions are accompanied by emission of radiation, therefore are called as radiative transitions. Spectroscopically, the transition from S1 to S0 state is an allowed transition and occur at 10 raised to the power minus 8 second. The emission of radiation in this transition is called as fluorescence. The transmission from the triplet excited state T1 to the ground state S0 is rather slow and a forbidden transition. The emission of radiation in this transition is known as phosphorescence. Both fluorescence and phosphorescence are the transitions are of shorter frequencies than the exciting life. This is because some part of the light energy absorbed by the molecule is dissipated in the form of heat during the non-radiative processes. Thank you for your time. These are the references I used for making this seminar. Again, thank you for your time.